Greetings, my name is Hadija Athman. I am working with Okello Andrew Peters on a study entitled The Computationally Efficient Breast Cancer Classification using Vision Transformers and EfficientNet. This is a hybrid approach with quantum genetic algorithm for region of interest selection and hyperparameter optimization. So a little bit of an introduction into the study we are carrying out, which is about breast cancer. So breast cancer is one of the most common cancers in women, with approximately 2.3 million women globally diagnosed annually, according to the World Health Organization. Early detection is important for improving survival rates, and mammography is still the global standard for screening. However, traditional diagnostic methods tend to be really slow and often prone to human error, which can lead to false positives and negatives. So a little bit of literature that we did in regards to breast cancer and the studies that have been done, we realized that there are so many studies that have been done using deep learning with exceptional results. So for example, CNNs such as ResNet, DenseNet, and MobileNet were applied in different studies and have shown excellent effectiveness in feature extraction and classification. Then also meta-heuristic algorithms such as the particle swarm optimization, gray wolf optimizer, among others, and genetic algorithms. Other genetic algorithms have been used for hyperparameter tuning and optimizations, as we shall see in the concept note. We have references. Then also some studies added emphasize on the region of interest, but then some traditional segmentation methods such as OTSU, UNet, and YOLO-based detection often suffer from false positives and computational inefficiencies. So our problem statement is that while CNN-based architectures have achieved high accuracy in breast cancer classification, they present major computational challenges and hinder real-time clinical deployment. Mammograms contain high-dimensional information, making deep feature extraction computationally expensive. Okay, Andrew will take one from here with the proposed solution. Thank you.
Thank you very much, Hadija, for highlighting the introduction and background of our study and literature review. So I'll be taking us through the proposed solution as it's clearly stated on the screen. We are going to leverage to use a hybrid approach that combines, for starters, the first one is EfficientNet, which extracts local features using depth-wise convolutions and compound scaling, reducing spatial redundancy before passing information to the vision transformers. So yes, we are using EfficientNet, and because if EfficientNet is a family of this diagram here, the diagram above, it's a diagram of the EfficientNet that we got from Google. So EfficientNet is a family of convolutional neural networks designed for efficient scaling and improved accuracy. It follows a compound scaling approach, meaning it scales depth, width, and resolution systematically rather than arbitrarily increasing layers of parameters. So it has these conv 3x3 filters, which so it starts with those filters which capture low-level features like edges and textures. Then it has this MB convolution, which I already explained what they mean. So those MB convolution blocks, they have depth-wise convolution where each input channel is convolved separately, reducing computation. There's also point-wise convolution, which uses a one-by-one convolution, which merges information across channels. Then the squeeze and excitation SE, which improves feature representation by reweighting the parameters. Yeah, next slide. So another thing that we are going to use is the vision transformer, which captures global dependencies using the self-attention mechanisms, enhancing feature representation for accurate classification. So for our study, we are going to use the Swin Tiny architecture because of the limited computational resources. Since we are going to use Google Colab to implement this hybrid solution, these diagrams at the right side of the screen, one is the architecture of the vision transformer. The first one, that is the patched image. So the vision transformer, the initial step of the vision transformer model reshapes the image into a sequence of 2D patches. So the reshaping allows the transformer model to treat an image as a sequence input and leverages the self-attention mechanism to extract relationship between patches. So self-attention mechanism captures, like, it excels in learning global adaptive length relationships. So that is why we are using it, because the transformer will captures the long range. Efficient net will be capturing the local patterns. And this other diagram, we pulled out the transformer encode and try to show its intestines. You realize it has the normalization. We have the multi-head attention, the normalization, then the multi-layer perceptron, which outputs the binary output. Yeah, proceed. So we're also going to leverage the quantum genetic algorithm, which optimizes hyperparameters, EG learning rate, dropout rate, the patch size, and refines the regions of interest selection to focus on the most relevant mammographic features. Next. First, go to the methodology abstract. Proceed to the next slide. I'm going to come back to this one. So before we talk about the computational issues, I wanted to first talk about our methodology as it's clearly visible. We start with the mammogram images, which are going to go through a vigorous, meticulous oversampling. We oversample the minority class to be the same as the majority class. Then we also do things like checking the contrast, the brightness, the artifacts in the images. We do some denoising. We also, if need be, we apply some filters and all that. So the output of the EDA is pre-processed mammogram images, which now go through the efficient net. So the efficient net, like I said, it extracts local features, reducing spatial redundancy, which outputs the feature maps. Feature maps are just 3D tensors. But remember, the vision transformer model, like, expects a sequence input. That is why these 3D tensors from the efficient net are then flattened and reshaped so that they are in that format. So the output of the flattening layer is the patched image or a sequence of patches, which then enters the vision transformer. So the vision transformer applies self-attention mechanisms to capture long-range dependencies and then outputs processed feature embeddings, which are just representations of these vectors, because inside the vision transformer, the sequence of patches are flattened into vectors, which is just a series of numbers, which are then mapped into higher dimensional spaces, which the vision transformer can understand. So these processed feature embeddings output by the vision transformer are then further processed by the quantum genetic algorithm. Inside the QGA, we first initialize the population. That is, we randomly generate initial parameters and regions of interest selections. Then we evaluate fitness But of course, we use the fitness score as our metric of measuring the fitness. Then we update parameters. That is, we apply quantum-inspired mutations and crossover. So it should be noted that quantum genetic algorithm does not use back propagation. For it, it uses its mutations and crossovers to do that. Then we do selection where we choose the best candidates for hyperparameter tuning and regions of interest. Then we output optimized hyperparameters and refined regions of interest, which then goes through the multi-layer perceptron. And a multi-layer perceptron is simply a network of densely connected layers where we apply non-linear transformation inside the hidden layers of the multi-layer perceptron. We use the activation function, which is ReLU, the rectified linear unit, to capture non-linearity. Then in the last layer of the multi-layer perceptron, we use the activation function called sigmoid to output a binary score, which is either malignant or benign. Yeah, that is what I have for the methodology. You can go back to that slide. So how are we addressing the computational challenges? The vanishing gradient, like I said, we are using ReLU. Vanishing gradient is where the gradient of the previous layers diminishes, whereby it makes it impossible for us to do back propagation. That means it makes it impossible for us to go back and update the weights depending on the score that is computed by the loss function. So ReLU helps us with vanishing gradient. Then the computational efficiency, we are using EfficientNet for feature extraction, which reduces dimensionality before these things enter into the vision transformer for processing, reducing computation overhead. Our optimization strategy, which is the quantum genetic algorithm, will be generated for hyperparameter selection and region of interest segmentation, improving convergence, speed, and classification accuracy. Yeah, that is what we had. The rest of the details are in the concept note.